let's learn how to wire up a button. To start with, I'm going to draw an Arduino. It's got a 5-volt pin, it's got a ground pin. I'm going to connect that to the other ground stuff, and the 5-volt I'm connecting to the other 5-volt stuff. Let's imagine we're still going to use pin 8, and I'm going to just say, well, what is a very simple way of installing a switch to provide power or ground to pin 8? Well, I could start by just saying, here's 5 volts, and here's a place I can put a switch, and there we go like that. Great, okay. Well, not so great. What's going to happen when this switch is open, and open means power is not flowing, is it's going to behave just like the wire did when we unplugged it from the power or ground. In other words, when the switch is open as currently drawn, pin 8 will see an ambiguous input, and you will maybe get highs, maybe get lows, you don't know, but it's not a reliable thing. When the switch is closed as drawn, no problem. You will have pin 8 connected to 5 volts, and it will definitely read high. Now you might be asking, by the way, hey, don't I need a resistor in there? No, you don't need a resistor when a pin is in input mode. When in the setup we say pin mode, whatever, 8, input, we're actually making an electrical change inside the Arduino that's essentially adding a very big resistor inside of there. So you don't need to worry about it. You do need resistors on pins which are outputs. So if you're driving an LED or a speaker or something else like that, yes, you do need a resistor. But in the case of an input pin, you don't. And please note, the schematic does not say whether this is an input pin or an output pin. That is actually configured in software. So no, you don't need a resistor there for an input. Now, we have to resolve this problem of the ambiguous moment when the switch is open and it's not connected to 5 volts, it's not connected to anything. You're going to get zeros and ones, highs and lows on pin 8. So here's one way we could solve that. I could attach on this side of the switch, I could make a connection and I could attach this to ground. Well, you might think, okay, that's an answer. When the switch is open, it's connected to ground. Now, what's going to happen when the switch is closed? Church bells will happen, naturally. What will happen is you will be connecting it as currently drawn. If you close the switch, 5 volts is connected through the switch down to ground. What happens when you connect 5 volts to ground like that with no resistor in between? Trouble. Big trouble. You can't do that because you'll be shorting out the Arduino. So apologies about the video freezing. It'll come back momentarily. So that's going to short out the Arduino, which is really a big problem. It's going to break. It's going to not turn on. It probably won't harm the computer attached to it, but it is actually possible to harm the computer attached to it. So we can't ever connect 5 volts straight to ground. So this isn't quite the answer, but there is a slight modification we can make to this to make it work. The slight modification is add a resistor. We're going to add the resistor right there. That resistor means that when pin 8 is, when the switch is open, pin 8 is connected to ground. Yes, it's connected through a resistor, but it's connected to nothing else. So the ground is definitely going to, that voltage will flow through to pin 8. The 0 volts will make it through there because there's nothing else affecting it. When the switch is closed, what will happen? When the switch is closed, which would look like that, 5 volts will be flowing into pin 8. Also, ground will be attached to pin 8. Also, 5 volts would flow down to ground, but the resistor makes a big difference. And in fact, speaking of big, we use a high value resistor. 10 kilo ohms, 10,000 ohms is the classic resistor we use in this case. And in fact, how much current is going to flow from 5 volts down to ground? Well, I invite you to do the math. I equals V over R. I equals 5 volts divided by 10,000 ohms. How much current is that going to be? 5/10,000ths. I equals 0.00005 amps. Not very much current. That is half of a milliamp. So yes, current will be flowing, but barely any, because that's a high value resistor. So this resistor in this position in a circuit, this is called a pull down resistor. A pull down resistor is not a special kind of resistor. It is a role that the resistor has in the circuit. And it's called pull down because consider what pin 8 would look like if we didn't have that there and we didn't have any of that stuff below there. It would be just kind of floating. And I think of it like a balloon with just the right amount of helium in it that is just sitting still. It's not floating up, it's not floating down. And the pull down resistor is a little string gently pulling it down. Gently pulling it down to ground. So if nothing else is affecting it, it'll be pulling it down to ground. Now, if 5 volts is attached to it, it will be 5 volts will be attached to pin 8 at the same time that ground will be attached through the resistor. Then I think of that circumstance is kind of like pin 8 is sitting in between two different things. On the left is somebody screaming 5 volts because 5 volts is connected to it with no resistance whatsoever. I'm sorry. On the right is, I guess you're right, is a little whisper, ground, little tiny whisper saying ground. So that resistor is what makes the shout into a whisper. Without that resistor, 5 volts would be shouting from the left, ground would be shouting from the left, and pin 8 would be kind of in the middle, and it would be unsure of which one to believe. It would be kind of confused. Also, we'd have that problem of shorting. With the resistor, problem solved. A screaming 5 volts over here, a whisper of ground over here, and the screaming 5 volts wins. Pin 8 will definitely be high when the switch is closed, and pin 8 will definitely be low when the switch is open. That is the beauty of this circuit. We don't have the problem of the ambiguous input. So it's actually a little bit more complicated to wire than the potentiometer was as an analog input, but the complication is necessary in order to do this properly. Now, in your kit, let's get to the actual physical wiring. There's 2 points we're going to have to make. One is, what does a 10 kilo ohm resistor look like? Well, in your kit that came with the micro course, there is a 10K label on a bunch of resistors. These are resistors. And actually, there is a color code on them as well. It's hard to see on this camera, but the colors on this resistor, I'm reading from the left here to the right, are brown, black, black, red, brown. And that code also encodes the number 10,000. So the colors actually do matter. So I'm going to take a 10,000 ohm resistor out of this little strip, and we're going to use it in the circuit. The other thing we're going to use in the circuit is this little push button. Now this push button is a little momentary push button, meaning when you push and it makes that little clicking sound, it is closed, and when you don't, it's open. It's got a little spring in it that bounces that thing back. But it has a very surprising internal wiring that I'm going to show you. It has, I'm going to get real nice and close so you can see this. The switch has 4 legs, not 2. If it had 2, we'd probably guess the wiring pretty effectively, but it's not. So what are we going to do? How are we actually going to physically wire up this thing? Well, we need to know how it works internally, and I'm going to show you how it works. I'm going to bend the legs out a little bit just to be clear that the legs have a side. They are not coming out of the corner. They're coming from the sides. And next to the switch, I'm going to draw a schematic about the same size as it, and I'm going to show you actually how it works. Yes, this is a tiny little drawing, but I'm making it the same size as the switch. There is a little baby switch inside of this switch. The upper left leg and the upper right leg, they are always connected, no matter what. There's a wire inside the device. The bottom left leg and the bottom right leg are always connected, no matter what. What happens when you press that button, make that little click, is that the top legs become connected to the bottom legs. So that is funny. That's a funny operation. It's not intuitive, but it's true. So how can we incorporate this little switch into our circuit up there? Well, I'm going to replace this switch as drawn with a drawing of our little push button switch. It's got a leg on bottom, a leg on top, and the switch operates across the middle. And the way I'm going to draw this is I'll say the upper right leg should connect to 5 volts and the lower left leg should connect to the Arduino side. So that, as drawn, is the totality of the wiring we're going to build. So now I'm going to bring an Arduino alongside the schematic. And yes, it's a little confusing to do this stuff at first, but we'll do it together and it's not so bad. I'm going to unplug my Arduino. It's always a good idea to do your wiring with the parts unplugged first, especially if you're not certain quite what's going on. So let's just match the schematic to the thing. A wire is coming out of pin 8. Check, we've got that. And it's going into some place on the breadboard. I'm just going to plug it in to here. It's a random row. In my case, it's row 17. Doesn't really matter. Just any random place will be fine. Now I'm going to take this little switch and I have to push button, bend legs in a bit so that they will sit properly on the breadboard. And I'm going to, and it's still oriented in the same way, I'm going to put it like this in the breadboard so that the bottom left leg of the push button is in the same row as that wire. Now, please note that by going across the middle, all of this row is connected through the switch, through the button, to all of this row. So all of row 17, usually the left is not connected to the right, but it's actually connected through this thing right now. Likewise, all of row 15 is connected to all of row 15, regardless of whether you're pressing this. You could be pressing or not. It's still going to be connected. So now the other side of the switch, which I drew in the upper right corner, is going to connect to 5 volts. I have a short red wire. Anytime I'm connecting anything to 5 volts, I use a red wire. So I'm going to put that wire in that row and connect the other side up to power. Okay. There's only one component missing, which is the resistor. So what I see from my schematic is that somewhere connected to pin 8 and connected to that little push button switch, I need to have a resistor that goes down to ground. So I'm going to take the resistor and bend the legs. I'm going to put one leg at that place where that dot is. When you see a dot on a schematic, a node, that frequently means that that is going to also be representable by a row in the breadboard. So I'm going to plug one leg right into that row, like that. Where does the other side of the leg go? The other leg, rather, of the resistor? Straight to ground. And actually, I can simply plug the other leg right down into ground. I don't need to use another jumper wire, or a black jumper wire, for instance. This wiring on the right matches this schematic on the left, and this is the proper wiring for a tactile push button. So I invite you, of course, to build your own, matching exactly this pattern, this electrical pattern. You don't need to choose the same row I do, but you do need to match the pattern. Otherwise, you will have a problem. When I press this button, pin 8 on the Arduino will see 5 volts, and when I don't press the button, it will see 0 volts. I know it took a lot of work to get here, but now you know how to wire a push button, and next we can actually use the push button in a practical way.